will be talking about the maritime industry today. It's about the application of the Arcadia method on a bulk carrier with Siemens Teamcenter PLM integration. What we will be talking about today is just a short introduction to our institute. So we are from Graz University of Technology, so not a company, but a university. Then I will introduce you to the context of our case study, which is the maritime industry, and in specific, its decarbonization and also digitalization. Then we will come to the interesting part of our talk today, to the most interesting part, I think, for you, which is the bike carrier system model integration into Siemens Teamcenter. And then we will have a short summary of what we have been talking about today. So, who are we? I am Matthias Dreier. I'm at the end of my master studies at Graz University of Technology, and I'm also a university assistant of the Institute of Machine Components and Methods of Development, and also a project engineer at Antemia GmbH. I have some experience in the automotive industry. Just to get that question away in the beginning, why we, as an Austrian university, are talking about the maritime industry is because our talk today is the continuation of my master thesis project, which I started in Japan during my exchange year there. So Japan is one of the three biggest ship manufacturers besides South Korea and China. So now you know why an Austrian university is researching about the maritime industry. And now for Matthias, I will hand over to him.
Thank you. I'm the other Matthias. I have a PhD in mechanical engineering, and I also part of the university, also at the same Institute for Machine Components and Methods for Development. And also in parallel to my university job, I also have several years of experience in automotive industry, and there especially in powertrain train development and systems engineering.
All right. So shortly to our institute, we are located, as I already told you, in Austria, in the middle of Europe. The most important thing about our institute is that you see here at this slide the V model with some pretty pictures of some test beds and our institute. Basically, we cover the whole V model at our institute. So from system design, from requirements, system architecture on the left side of the V, to the domains at the bottom, mechanical, electrics, electronics, software, until integration and verification and validation. So the whole V is covered at our institute. So for the two big columns of our institute, which is machine components, it's about, as you can see here, bearings or the transmission itself, e-motor, and so on. And for methods of development, it's systems engineering, model-based systems engineering, process methods, development platforms, digital twin, you name it. We basically do all of that at our institute and do research for academia and the industry, and also projects. So yeah, as I told you, just a short overview of our institute, and then let's dive right into our talk, the context, which is the decarbonization and digitalization of the maritime industry. So what is the maritime industry? Just some pictures for you to get an idea. All of you know it. Maritime industry, and specifically today, I'm talking about the shipping industry of the maritime industry. You can see a bulk carrier transporting coal or wheat in bulk cargo, or of course container ships. We all know them on our oceans. And in the context of decarbonization, here you can see that the marine shipping contributes to around 11% of the global transportation well-to-wheel CO2e emissions. This transportation sector itself is about 1/4 of global anthropogenic CO2e emissions. So it's quite a lot. And as we all know, we are in a climate crisis and we need to decarbonize fast and implement solutions fast. And every industry is working towards that. And now we will have a look how the maritime industry is doing regarding that. For example, also about MBSE in the maritime industry, just to give you an overview, compared to other industries, how they use it, they practically don't use it at all. So here in the study of INCOSE from 2018, you can see at the other category, there is the maritime industry in there, and itself, this category, it's not even mentioned. So according to this study, which is based on a questionnaire back then, MBSE is not used at the maritime industry at all. So what is the challenge of marine shipping? So we have two challenges that are in contradiction to each other, basically. First of all, we have which is not a challenge, but actually the mission of the maritime industry. Its mission is to transport goods, resources, and passengers. And the two challenges are, on the one hand, the decarbonisation, which is in contradiction to legislation and costs. So if you want to decarbonize, you have to have the legislation for that, and you have to pay for that. And also, shipping needs to be on time. But if you ship faster, you emit more CO2 emissions. So that's also contradictory to each other, and also market. And just to give you an overview, what is the current plans in the maritime industry to decarbonize? The International Maritime Organization, which is the most important organization for regulatory suggestions actually in the industry, has its 2023 IMO greenhouse gas strategy. As you can see here on this slide, the business as usual would be the above straight line, and then strategies of 2018 and 2023, which is a revised one, you can see here. So basically, if you don't do anything, it's business as usual, and the plan is to get net zero greenhouse gas emissions until 2050, which is not far away. So no measures, the targets are not reached. And in the industry, you have a lot of stakeholders, and here I will show you just a little stakeholder value network to give you an overview how many stakeholders there are. And if you want to reach those targets to decarbonize such a big industry with so many key players, so many countries, and so many stakeholders, that's not an easy thing to do. So as you can see, there's a very big value flow between those stakeholders. Regarding the technical solutions to decarbonize, just to give you an overview, basically what you can see here are three different types of solutions, which are low and zero emission alternative fuels and propulsion technologies, such as wind assistance devices or highly efficient engines and alternative fuels, also energy saving technologies, and also operational measures. And what is important about this slide is that the system, in this case, a ship, has to be considered as a whole to achieve greenhouse gas reduction, which is often forgotten if you think about decarbonization, because just using alternative fuels will not lead to a full decarbonized ship. And the focus of this case study is also the wind assistance devices. We'll, on the next slide, then explain what these cylinders are. They are called Flettner rotors. And basically, there are a lot of different wind assistance devices. So we are going full circle now. We had sailing ships, and now we are going back to them, because it's actually quite a good idea to save fuel. So as I said, here you can see on this bike carrier, this is a picture from 2018, 4 Flettner rotors. And the basic principle, just for you to understand, the wind is hitting the cylinder, which revolves, and due to the Magnus effect, a forward thrust is generated. So it's quite a basic physical principle. All right. Now, so much to the context of this case study. And now to the example, what I've been doing in my master thesis and then in the continuation at our institute and our talk today. So the shipping industry uses quite a simple ship development process, which you can see here, which is called the design spiral. It's a spiral process. I'm showing you this slide just to give you an idea how ships are developed at the moment and why that is not suitable for zero emission vessels and the vessels that need to be developed and retrofitted to achieve greenhouse gas reduction, for example. So at this development process, the focus lies on the design and the main functions of the ship. So it's purely, basically just a mechanical development process. And the challenge with these design-heavy processes is that the problems with an increasing proportion of mechatronics, so control systems and so on, leads to a big challenge. Also, operations are only briefly described in the beginning and then not anymore. So we propose as a proposal another approach to this. So MBSE with Arcadia and Capella. Here you see the Arcadia method. I think most of you are familiar with that. We link that with the V model, which everybody of you probably is also aware of, which is a procedure model for the development of mechatronic systems. And due to the increasing share of the mechatronics, we propose that model. Also, and we expand and link it with the Arcadia method and the SMW system model, or the Capella system model. We end with product lifecycle management and the processes, methods, organization, and the tools. We'll then go straight into our case study now. What you will be seeing in the next minutes are always some schematic diagrams to give you an overview of the system model we have created, because the actual system model is too large to show in slides. So, as you know, operational analysis, first one of the Arcadia method. Here you see the context and the challenge of the maritime industry I showed you before. So the decarbonisation versus legislation and so on, and environment versus market demands. And here we link that with our operational entities, which are basically the stakeholders from our stakeholder value network I showed you before. So we can divide them to regulatory organizations and public institutions and also private companies. And all those stakeholders, as also shown before in the stakeholder value network, just briefly, are in relation with each other. So, for example, the International Maritime Organization, IMO, provides regulation to the government and so on. And the classification society, also a very important stakeholder, the maritime industry, provides classification and service to shipbuilding company or shipping company and so on. So in this phase of the Arcadia method, we don't look at the system of interest, but at the stakeholders that are interested in the system of interest and their operational capabilities that you can see here in green, what they want to do with the system of interest. So we focus on understanding the needs from the perspective of operational users with the targets of identifying their needs, activities, and their interactions. And how does it look like in SMW? You can see it here. That's our operational capabilities diagram. For example, an excerpt here, again, the shipbuilding company that has its operational capability to build zero emission vessels. All right, then going to the system analysis. Here you see the bi-carrier system for the first time in the middle. And now all those operational entities are now system actors and are around the bulk carrier system. And what we do now, we want to understand how those operations are linked with our system of interest. So the system analysis focuses on identifying a system that's capable of meeting the identified challenges. Again, here just to show you some exchanges between those system actors with our system of interest and with them with themselves, and now also some system functions. For example, again, for the International Maritime Organization at the left upper corner to provide regulation. But I will not go into detail because that will really be too much for this talk today. And how does that look like in SMW? For example, on the left side, you see the mission, which is also a part of the system analysis to identify the mission and the capabilities of the system. And here on the right side, you see in the middle the system and around the system actors. So you get an idea. It's quite a big network of exchanges, functions, and flows in the shipping industry around the bulk carrier system. Going to the logical architecture, which now considers the internal logical structure of the bulk carrier system. As you can see here, now the system of interest is looked at in detail without technological options. So for example, propulsion and power generation is one subsystem. Again, with some example logical actors that are also again in relation with our system, have their own logical functions, and now also functional exchanges. For example, you see the generate and store electric power function of the propulsion and power generation system has a functional exchange to the environment with CO2 over the combustion exhaust flow, just as an example how this is modeled in Capella or SMW. And how does this look like in SMW? Again, a logical architecture diagram. And you can see here it's a little bit too small, but what we did here is we wanted to integrate the greenhouse reduction solutions you saw before with the bulk carrier and then the options. We wanted to integrate those logically to the existing subsystems of a bulk carrier. So this is actually what such a system architecture diagram is useful for, to get an overview which might be in your head, which might be trivial, but it is not. Modeling such a logical architecture diagram with the available solutions gives you an overview what subsystem or what function is affected by what solution. So this is pretty useful for that. Now to the last phase of the Arcadia method of today is the physical architecture, which now defines the system and its subsystems from a physical point of view. It's quite similar to the logical architecture, but now we will going way more into detail. So our system of interest, the bulk carrier, has now much more subsystems, and also they have subsystems. For example, propulsion and power plant with a main engine and propeller and so on. Again, physical actors, and they're again in relation with our system of interest with component exchanges, and they have functions that have functional exchanges and also physical exchanges. So for example, if you look at the main electrical power supply, here at our system in the middle is connected with the bridge system with cables as a physical link, and the component exchange is electrical power transfer, and they exchange electrical power. So that's just the way the Arcadia modeling language and Capella works. So the focus of this project is to integrate wind assistance devices into existing bulk carrier vessels. So thus the subsystems and components that interact with the wind assistance device are modeled in greater detail, which is not shown here on this schematic overview of the physical architecture. But on the next slide, you see this resulted in quite a big system architecture diagram, the physical architecture, which basically shows all the subsystems of the bulk carrier. What we did is we modeled and connected all relevant subsystems and functions. We considered the physical actors on the left side in blue, you can see here, and defined all the interfaces and exchanges we deemed relevant for the integration of wind assistance devices. I will now go, here you can see, for example, the auxiliary propulsion is one of those subsystems with the 4 flattened rotor sails. So the physical architecture diagram is really helpful to, for example, if a naval engineer needs to manage all the interfaces between the subsystems, he or she can do that using the physical architecture. So here we integrated the flattened rotors to the bulk carrier system, and we have now a structural, hierarchical, and a functional view of the system, which can be used as a basis for integration, verification, and also validation. Now, I know that was a lot. Probably most of you know the Arcadia method and their diagrams, but this was, after all, the main part of our case study to apply model-based systems engineering on the maritime industry. But now the very interesting part. So what can you do with that? So the product development with MBSE and PLM, I will show you. So how can it be used? For example, you can use it to align all the discipline-specific development. So it serves, the system architecture serves as a great basis to share the knowledge with all the disciplines. But to really be able to use your system architecture, your system model, you need a product lifecycle management system, which connects all those disciplines with your descriptive system model and can be used for data management, workflows, roles, and permissions. And that's what we have been doing. So here you see our very simple workflow of our project. After the creation of the SMW architecture with the 4 phases that I just showed you, we uploaded the architecture to Teamcenter. We then reviewed the architecture and released it. And then we created requirements and test cases. So in the maritime context. And then as a last step, we linked those system artifacts in the environment of Teamcenter. And how does that look like in Teamcenter? You can see here requirements. Maybe I hope you can read it a little bit, but on the left side, you see, for example, the cargo type. You can use Teamcenter, or as the colleagues before showed in Polarian, to create your requirements and then link them with your system artifacts to achieve traceability. And how does this traceability look like? For example, in Teamcenter, you can see here in the middle, with you see the physical components, which is in this case the auxiliary propulsion control system, which has 3 functions modeled in our physical architecture. You can see here at the bottom, and we linked it with the requirement, the safety mechanism of the rotor sails, and the test case, the heavy weather deactivation test case. So the Teamcenter product lifecycle management system can be used to manage your artifacts traceability effectively. And here on the next slide also, you see the logical architecture directly in Teamcenter. And why is that important? If you only have your logical architecture, for example, in SMW or Capella, probably only the systems engineer will take a look at that. As we all know, it's sometimes quite hard to get the discipline-specific experts, for example, mechanical engineer or electrical engineer to really understand the value of such a system architecture. But with providing and making it accessible in the Teamcenter product lifecycle management system, you can bring the disciplines together early in development using this system architecture, which is probably easier than not having it in your product lifecycle management environment. So do not just document what has already been built is our approach to that. And with that, I'm already at the end of our presentation, and we'll now go into our summary and an outlook. So what have you been hearing now? The maritime industry is confronted with increasing complexity. So the emissions and fuels, as well as like the routing optimization, automatic cruise functions, and so on, are many topics that are discussed. And the development of zero emission vessels requires new approaches. And the current approaches are, in our opinion, just not fit for the challenges. So model-based systems engineering is an approach that should be used to tackle these challenges. For example, to retrofit the existing fleet with greenhouse gas reduction solutions like wind assistance devices. And of course, despite its low level of adoption of MBSE in the maritime industry, as I've showed you in the beginning, its application is not only beneficial, but is essential in our point of view. So it can enhance the communication between a large number of stakeholders, for example, and provide a deeper understanding of the complex system and supports in the integration of new technologies, for example, wind assistance devices. Some challenges can be, for example, to evaluate where is the value in applying MBSE to really make the value understandable for the stakeholders, which is often a challenge, although we as systems engineers know where the value lies. And we also have to adapt existing processes and methods and introduce new software tools. And also the organizational structure has to be adapted with new roles and responsibilities. So the modernized development approach with Arcadia and the V model is our suggestion how to apply MBSE in the maritime industry. So to go from the sequential ship design spiral to a concurrent engineering using the V model and the Arcadia method. And I want to end now with the last sentence, which is MBSE in the maritime industry is a must. And with that, I thank you for your attention, and Matthias and I are open for your questions. So thank you very much.
So we are getting some questions. So let me start with the first one. So one question regarding configuration and change management. So are you granting full configuration and change management of the product with this solution? So I think, as you are using Teamcenter as a PLM, probably that's why this question.
Yeah, of course. Especially with Teamcenter, this is possible. For example, in Teamcenter, we can create change item and allocate all affected items to this change item, so we can track, for example, when other items are part of this change and manage this via this change item. We can also assign this to a dedicated workflow to really keep on track and also align all the let's say all the engineers which are necessary as step by step for this specific workflow in case of a change. So with Teamcenter, in that case, it is possible.
Let's see the other. So other two questions. So one, so about the method. So what do you call physical function? So in your case, for in the slide about the model integrated into Teamcenter, so the the SMW view, the physical architecture, I think. So if you can give some examples, probably, and what is a physical function in your domain? Yeah.
Yes, of course. I will share my screen again to answer that question. For example, a physical function, yes. Here, I think it's better to show the schematic view of the physical architecture diagram. For example, the physical function is for the bridge system to control the power generation and propulsion, or to navigate and steer the ship, just as two examples. Or for the subsystem of main electrical power supply, the main function, physical function, is provide and distribute the electrical power. Yeah, those are some examples.
Yeah, maybe to add here one comment, we really tried to focus on the main function, because of course, when you also include all the secondary functions, there are many more functions allocated to the physical elements. And then the model itself really explodes also all the relations between the functions. And to avoid this a little bit, we really try to focus on what should this physical component really do. And of course, this is part of our further research activity to also start detailing the model with all the secondary functions.
Yes, thank you, Matthias.
Great answer. Fully agree also on your approach. Another question, so it's more on your domain, but so not very specific for Capella, but let's say for your context, your model. So is nuclear propulsion considered as a decarbonisation solution in the maritime transportation? Yeah. If no, why?
That's
I don't know if you can give your insight. Yeah.
That's a good question. I myself am not a naval engineer, but I know the answer to this question because I encountered it in my research about the options, how to decarbonize shipping. Nuclear propulsion is not an option for the non-military shipping, because it will just not be accepted by the general public to do that. And also, you see, it happens that, for example, an oil carrier or some container ships, they also nowadays, they have accidents and they sink and they have environmental problems, for example, oil pest or something like that. You can only, and that's very bad itself. And you can only imagine if that happens with a very big vessel that has a nuclear reactor on board. If there is an accident, this will not look too good. So that's why nuclear propulsion is only used in naval military applications in my experience, what I've seen.
Thank you, Matthias, for the answer. So another few questions are there. Let me show you. So a great clear presentation. I totally agree. So how do you map EVV requirement in the model? Is it by also using artifact? I think you show very quickly a test object, if I'm not wrong. So yes, please.
Yeah, in that case, we manage this via Teamcenter, because there, at our configuration, there are a lot of different artifacts available. And one of them is, for example, the test case, but there are also more such as the test procedure, the test method, or also customized items. And so besides the artifacts we modeled in SMW, or the rest, or the different kinds of requirements and test cases, we created as artifact in Teamcenter.
Great. I think it answered the question of Joao. Another question. 1 second. Okay, next question from Ruben. So good presentation again. So can you comment about the benefits of system modeling, even without documentation during build, allowing integration and compatibility between subsystems? So how you manage system, subsystem, and without documentation, let's say, or less documentation?
Of course, what we realized during modeling this architecture, of course, we by ourselves learned a lot about how this bulk carrier is working. And of course, Matthias undersold himself a little bit. He was in Japan and talking with leading experts of maritime industry, and so he gained a lot of knowledge. And what we tried is with our modeling activities to bring this knowledge into the model. And Matthias saw there that a lot of information on one hand is in the brain of all the experts there, and also distributed to several documents. So this was one activity, but also for the developing itself, what we realized that architecture is more than just documentation. It is really a collaboration in your development process, so a collaboration tool in your development process.
That's totally true, and thank you for the compliment. In my experience, also, you use if you have an architecture of your system, even a very basic one, it really helps to streamline and ensure correct communication in the beginning of development projects. For example, we had a student project at the university where we developed a transportation system out of Lego building blocks with controllers and actuators and electric motors, and bringing the development of all disciplines together. And we worked with the system architecture from the beginning, which really helped to know what are our subsystems, what are the functions they have to fulfill, how are they connected, how are they controlled. So in our opinion, using something else than a system architecture is just not so efficient for developing the system.
Yes, I totally agree with your answer again. So can add even in Thales, that's our approach. So of course, it doesn't replace documentation, but it structure everything, it structure the activities. It's a common view for everyone. So yes, totally agree with your points of view. I think there is another question that is coming. So yeah, I don't know if you use this functionality, but how do you manage versioning in the model with Teamcenter requirements? So did you use these functionalities, or you, let's say, you tested?
In this case study, we only had one version, as I showed you in our very simple workflow. So we created the system, the descriptive system model of the bike carrier in SMW, and then we uploaded it to Teamcenter to show how to link all those artifacts from the system model with artifacts from verification and validation, such as requirements and test cases. So I think, Matthias, please help me, but you can handle the versioning in Teamcenter, of course, but in our case, there was no need to do that.
Yeah, that's exactly the answer. So yes, of course, it's possible. We do it for other projects, but for this demonstration here, it was not necessary to also use different versions. Yeah.
I noted one on my side. Did you share with let's say industries your work? I mean, naval company. You mentioned someone in Japan.
Yes.
Yeah, because I think it's very interesting to show to the companies that are working on that.
Yes. We did it. We shared this work. For example, a big part of also the talk today we presented in July at the INCOSI International Symposium, which we did together with my Japanese professor. He is one of the leaders of the Mode Lab at the University of Tokyo. The Mode Lab is a lab called Maritime and Ocean Digital Engineering Laboratory, where the biggest shipbuilding companies, classification societies of Japan come together at the University of Tokyo to research and develop solutions for the digitalization and decarbonisation of the future ships. And it's a 5 years project there. So I'm still in contact with those guys, and I'm sharing our research results with them, hoping to get more and more into a collaboration. Because in my experience, systems engineering and model-based systems engineering, especially in Japan, is seen a little bit differently than we see it here in Europe, maybe also at Thales. So in my opinion, they need those approaches. So we are working towards a collaboration with them.
Great. Yeah. Thank you very much.
Thank you. You too. Bye.